Hello everyone. Welcome back to the DDLC Seminar series by the Ideas Lab. I'm Nishant, and uh, for today we have Dr. Aditya Mahajan, and he's a little bio on Dr. Mahajan. He's a professor of electrical and computer science engineering at McGill University in Montreal, Canada, and he's a member of the Center of Intelligent Machines International Laboratory for Learning Systems and Gerard. And he got his BTech degree from IIT Kanpur and his master's and PhD from UMich. And then he held a visiting appointment at the University of California, Berkeley, and University of Paris, Saclay. And right now, he is a senior member of IEEE and a member of Professional Engineers Ontario, and he serves as the associate editor of IEEE Control Systems Letters and Springer's Mathematics of Control Systems and Signals and Systems. And before this, he has served as an associate editor in Transactions on Automatic Control and the IEEE Control System Society Conference Editorial. And he has received the 2015 George Axelby Outstanding Paper Award and the 2016 NSCRC Discovery Accelerator. And as an advisor, he's obtained the 2014 CDC Best Student Paper Award and 2016 Access Best Student Paper Award. And his principal research interests include decentralized stochastic control, team theory, reinforcement learning, multi-arm bandits, and information theory. And personally, I've come across some of his excellent work on common information approach and approximate information states. And I'm really excited to listen to him today. And without further ado, I'll pass on the mic to Dr. Mahajan.
Thanks, Nishant, for the introduction, and thanks to you and Andreas for the invitation to speak here. I'm going to talk about sort of a series of work that we have done over the last few years in terms of understanding how do we design agent state-based policies in partially observed MDPs or POMDPs, and in particular going beyond belief state MDPs. In part, this is based on a tutorial that we gave this CDC on the same topic, and you can look at this QR code to get the tutorial, or it's available on IEEE, or would be available on IEEE, I believe soon. I must start with acknowledging my co-authors on this work, Jayakumar Subramanian and Amit Sinha, who were Jayakumar was a former PhD student, and Amit is a PhD student who's graduating soon. So most of what I'm going to present is based on their thesis, as well as sort of other students I've worked with, Irfan, Nima, and Tianwei, and also collaborators Matthew Geist and Pierre-Luc Bacon. And this work was funded by NSERC and D&D through the IDEAS program. So the motivation here is that, as all of you would be aware, there have been many recent successes of RL. We know AlphaGo, learning to play arcade games, robotic graphing, and many, many others. And this success is based on algorithms which are based on comprehensive theory. However, for the most part, the theory is restricted to systems with perfect state observations. But when we look at other real-world applications, many things are partially observed. For example, healthcare, autonomous driving, finance, retail and marketing, and many others. So the question is, how can we develop a formal theory for reinforcement learning for such partially observed systems? So in this talk, I'm going to start with a background overview of MDPs and RL. This is primarily to set the notation and terminology. I'm going to present a quick review of the classical solution for partially observed MDPs and try to highlight why RL for partially observed MDPs is difficult. The main talk is split into two parts. First, I'm going to talk about what we call agent state-based planning, briefly discuss what are different agent state-based policies and different policy classes, and talk about ways of doing planning for each of the policy class, and then talk about agent state-based learning, in which we'll use ideas from planning to develop Q-learning and actor-critic style algorithms for the case of learning. So let's start with the background. And by the way, in case there are any questions, please feel free to interrupt me in the middle. So let's start with what's known as a Markov decision process. Markov decision process is a setting in which we have an environment which evolves in a Markovian manner. I'm going to use ST to denote the state of the environment, and it evolves according to some controlled transition matrix. The agent gets perfect observation of the state. So the agent observes the state ST. It takes some action AT. And when it takes an action, it gets a per step reward, which I'll call RT, which depends on the current state and action. And in principle, the action can be chosen as a function of the entire history of past observations and past actions available at the agent. This could also be a randomized function of the history of past observation and action. The collection of all these decision rules is called a policy, and the objective is to choose a policy to maximize the expected discounted reward under that policy. There are other optimization criteria as well, but I'll restrict myself to expected discounted reward setting in this talk. So there are two main conceptual challenges. One, if we try to solve this problem via brute force search over all policies, then the search has an exponential complexity in time. So the question is, how can we efficiently search and find the optimal policy? Classical results in MDPs rely on two simplifying ideas. The first is Blackwell's principle of irrelevant information, which states that there is no loss of optimality in choosing the current action as a function of the current state. The second is Bellman's principle of optimality, which says that essentially we can search for an optimal policy in a sequential manner. In particular, for the expected discounted reward problem, we can write a fixed point equation, and the solution to that equation tells what the optimal policy would be. Now, in the reinforcement learning setting, or sort of at least the online RL setting, which I'll focus on, the idea is that we are in a system where the dynamics and the reward functions may be unknown. However, the agent can interact with the environment. And when it interacts with the environment, it gets the same observation and rewards observations as before. So it observes the state. In addition, it is assumed that it can observe the rewards which are generated in the environment. And the objective is to design an algorithm or design algorithms which will asymptotically identify the optimal policy or an optimal policy. And broadly speaking, reinforcement learning algorithms can be divided into two groups. First is value-based methods, where one estimates a Q function and using temporal difference learning or other variants of stochastic approximation, and identifying a Q function is equivalent to having identified a policy which is greedy with respect to this Q function. This goes back to the work of Watkins and Dayan in the 90s, and Fitzsimmons and many others. The second idea is using policy-based methods, where you assume a parameterized policy, compute the gradient of the performance of that policy at a particular start state using a single trajectory. This is similar to the ideas of infinitesimal perturbation analysis. And again, there are many works which have looked into this, both in the computer science and the control community. Now, let's try to understand why is it difficult to extend these ideas in partially observed setting. So first, let's look at the model for partially observed MDPs or POMDPs. So the basic setup is same as before, but the key difference is that the observations made by the agent are now some noisy version of the state. So in the simplest setting, let's just think the observations are state plus noise, but it could be something more sophisticated as well. The rest of the model remains exactly the same. The agent chooses a action as a function of the history of its observation in past actions, receives an instantaneous per step reward, and is interested in maximizing the expected discounted total reward. Just notation, I'm going to be talking about different classes of policies. So when it gets to POMDPs, I'll start using pi vector to mean policies which are a function of the entire history. Now, again, the conceptual difficulties are same as before. We want to find the history-dependent policy that maximizes this. The size of the policy class is increasing exponentially over time, and we want to understand how to solve this efficiently. The classical solution relies on fundamental ideas from control theory, which is for such a system, we can identify a belief state, which is the posterior distribution of the state of the environment conditioned on the observation and actions of the agent. The belief state evolves in a state-like manner. This is known as the nonlinear filter, and that the belief state is sufficient to evaluate per step reward. And what this effectively means is that the belief state is a perfectly observed controlled Markov process. This has been shown explicitly in the work of Estrom in the 60s, but the ideas goes back to nonlinear filtering in the early 60s. Now, since the belief process is a controlled Markov process, we can just use the standard results from MDPs. So we can choose the current action as a function of the belief and write down a dynamic program as with the belief as the state. So there are two implications of this type of modeling framework. One, that sort of using beliefs allow us to use the MDP machinery for POMDPs. And there is a rich literature on various exact and approximate algorithms which efficiently solves this DP. However, when it gets to learning, things are not so straightforward. The key challenge is that the construction of the belief state depends on the system model. So if we are in a setting where the system model is unknown, we cannot construct the belief state, and therefore we cannot use standard RL algorithms. Now, the literature on learning for POMDPs is broadly sort of split on the theory and applied side. On the theory side, there are various alternative methods that have been proposed, such as predictive state representations, biosimulation metrics, and many others. They have good theoretical guarantees, but the challenge is to scale them to large-scale environments, and the difficulty basically boils down to that these methods cannot easily leverage the huge advances that we have had in neural network-based deep learning methods. On the practical side, a lot of research has ignored the theoretical difficulties and simply said, well, let's just do something like stack previous K observations and treat it as a state. We know it's not a state, but anyway, let's treat it as a state and run standard algorithms. So in practice, what it means is in a deep RL algorithm, instead of using a convolutional neural network, we just use a recurrent neural network and leave rest of the algorithm the same, do parameter tuning, and in most cases, this thing works. So we lose theoretical insights, but overall things are working. So our motivation for looking at this is, can we have some sort of understanding on why these deep RL algorithms are working for POMDPs? And based on this understanding, can we see how to perhaps improve these algorithms? And the main observation on which this direction of research lies on is that effectively, if I'm using a recurrent neural network to train a policy, the actions are being taken as a function of the state of the RNN. And in general, the state of an RNN would not be a belief state. It is just some state which the agent keeps track of. We call such states agent states. So in order to understand what's happening in deep RL algorithms of POMDPs, it's important to understand what is happening when we look at agent state-based policies in POMDPs. So let me sort of present an abstract model of what I mean by an agent state policies. So we consider POMDPs same model as before, but now assume that the agent has a state. I'm going to denote this state by ZT, and the state is evolved in some recursive manner. So the state at time t plus 1, zt plus 1, is some function of zt, yt plus 1, the observation that the agent gets at time t plus 1, and action at. An example of such an agent state would be an agent keeping track of its last n observation and actions, which is what is done in frame stacking. We could have something like a finite state controller, which could be an automata, which keeps track of an internal state of the agent or the state of a recurrent neural network. I'm going to use the notation HT to denote the history of observation and actions. And since the state is recursively updateable, the state at time t is some function of the history until time t, and I'll denote that by sigma vector t. So there are three fundamental questions in this setup. Are there instances when there is no loss of optimality in restricting attention to agent state-based policies? Second, if I give you the state space in which this agent state-based policy should lie, and the state update function, can we identify the best agent state-based policy within this class? And second, if I just give a size of the agent state, can I find the optimal state update rule and the optimal agent state-based policy? So question 2 would correspond to a setting where, let's say, I'm using frame stacking and I know what my agent state update function is. And question 3 would be something like where I'm using RNN, but I have not fixed the weights of the RNN, and I also want to learn what the optimal weights are. So the answer to the first question is a fundamental idea in stochastic control, the idea of an information state. Roughly speaking, an agent state satisfies an information state if it satisfies two properties. The first property is that the agent state should be sufficient for performance evaluation. That is, if I look at the expected value of the per step cost conditioned on the history and the agent state, that should be some function, history and the action, that should be some function of the agent state at time t and action. And second, that the agent state should be sufficient for predicting itself. So if I look at the distribution of the next agent state conditioned on the history and action, that should be some function of the current agent state and action. So there should exist a reward function and a dynamic functions which satisfy these two properties. And essentially, if I have a reward function and a dynamics function, I can write down a dynamic program. And the main result is that if we write an information state-based dynamic program, the corresponding policy would be optimal for the POMDP problem. So we can unroll it to find a history-based policy, which will be optimal. So some examples of information state is if I look at an MDP, then the current state is an information state. If I'm looking at POMDPs, then belief state is an information state. In specific models, such as linear quadratic Gaussian models, one can show that just the conditional mean is an information state, and there are many other examples in the literature. However, some non-examples of information state is the last observation. If we just use reactive policies in POMDPs, they are not based on an information state. If we use a window of last observations, as in frame stacking, that is also not an information state. Recurrent neural networks are not an information state. So everything which people are using in practice for these deep RL algorithms are not information states. So when things are information state, we know we get a dynamic programming decomposition and everything is nice. But what we really want to understand, if we want to understand deep RL algorithms, is what do we do if the agent state is not an information state? Okay. Before I go further, are there any questions so far?
No, Dr. Mahajan.
Thanks. Okay. So the main difficulty is that dynamic programming decomposition does not work if I do not have an information state. So let me try to explain at a high level why this happens. So the general idea of dynamic programming decomposition is that I'll write a dynamic program as a function of the current state. And this would be, I want to minimize over the set of actions, the current reward plus the future reward. You would use the towering property of conditional expectation to say that the future reward conditioned on current state and action can be written as the expected future reward conditioned on the next state, and then conditioned on the current state and action. And this expected future reward conditioned on the next state is the value function at the next state, which gives us the dynamic programming decomposition. However, when the agent state is not an information state, the sigma algebra generated by the current state and action is not a sigma algebra generated by the next state. Think of frame stacking. I'm losing information when I go to the next time. So since there is no nestedness of information, one cannot use smoothing property of conditional expectation, and therefore the standard DP argument breaks down. So if DP breaks down, there are a lot of other things which we take for granted in the MDP setting, which break down. To highlight that, I'm going to talk about different policy classes for different policy classes when we're thinking of history-based policies. So I'll use the notation capital pi vector NS. To vector means it's history dependent, and NS means it's non-stationary, N means it's non-stationary, S means it is stochastic policy. And we can think of vector ND, which is history-based, non-stationary deterministic. And I'll use the notation J vector star NS to mean the best policy within that class, and similarly J vector ND star to mean the best policy within the non-stationary deterministic class. Now, a standard result in stochastic control is that we can restrict attention, when we are looking at history-based policies, we can restrict attention to deterministic policies. There are various ways to prove that. Sort of a simple thing is this is actually a special case for a similar result, which holds in game theory known as Kuhn's theorem. But when we get to agent state policies, we don't have this. We can talk about general non-stationary stochastic agent state-based policies. The difference here would be that the policy at time t can only be a function of the agent state at time t. We can have non-stationary deterministic policies, or we can have stationary stochastic. Stationary means that the policy at every time is same. I can have stationary stochastic or stationary deterministic. And I'll use J star without the vectors to mean the optimal within the corresponding policy class with the corresponding subscript. Now, there is a set valued relationship between these different policy class. In particular, stationary deterministic is a subset of stationary stochastic. So the best performance in stationary deterministic will be less than equal to best performance in stationary stochastic, and I'll denote that by this arrow in this commutative diagram. Similarly, we know that non-stationary deterministic is a superset of stationary deterministic, so the performance would be no worse than this, and similarly for non-stationary stochastic. And since agent state-based policies are a subset of history-based policies, we have the next relationship as well. And what Kuhn's theorem tells us is that at the last level, when we are thinking of history-based policies, deterministic and stochastic perform the same, but we are interested in agent state-based policies. So when the agent state-based policy is an information state, from standard dynamic programming results, we know that stationary deterministic policies performs as well as non-stationary stochastic history-based policies. So these two extreme points in red are identical, so everything in middle is also identical. But when we do not have when the agent state is not an information state, these inequalities can be stripped. I'm just going to present few examples to show that stationary deterministic policies can be strictly worse than stationary stochastic, and stationary stochastic can be strictly worse than non-stationary deterministic. So let's consider an example where my state space is the set of integers. The agent gets an observation whether the current state is an odd state or an even state. And the odd states are shown in gray here, and the even states are shown in white. The reward function is such that in the states which are shown by red, agent gets a reward of 1 if it takes an action 0, and then it moves one step to the right. However, it takes the action 1, then the state resets to the first state, and it gets a reward of -1. In the non-red state, the behavior is reversed. So what the agent has to do is it has to figure out in every red state, I have to take action 0, and in the non-red state, I have to take action 1. But all that the agent observes is whether it's in the even state or the odd state. So it's clear here that there is an optimal non-stationary policy, and that non-stationary policy says at time 1, take action 0, because I know I'm going to be in a red state. I'll deterministically move to state 2, take action 0. I'll deterministically move to state 3, take action 1. I'll deterministically move to state 4. So I can just take the right sequence of actions. It keeps on moving me to the right, and I keep on incurring the reward of 1. So the expected discounted reward would be 1 upon 1 minus gamma. Now let's look at the class of stationary deterministic policies. There are only a finite number of those. We can explicitly list them, find the performance of the best of them, and that's given by this expression here. And we can do some simple algebra to show that for all discount factors, stationary deterministic policies are actually strictly worse than the non-stationary deterministic. In this particular example, through simulations, we can also compute the performance of stationary stochastic policies. And we find that stationary stochastic policies do the same as stationary deterministic, and therefore are strictly worse than non-stationary deterministic. So this is in contrast to MDPs, where there is no loss of optimality in restricting attention to stationary policies. Now let's consider another example. This is a simple 3-state MDP with some rewards and dynamics. I'll not try to parse this completely. The key point is that in this case, the agent gets no observation. So it just has to choose 2 actions, either action 0 or action 1. So I can parameterize class of all stochastic policies by the probability it chooses action 0. For that, I can do simple, I can do policy evaluation, but let's say I just do this with Monte Carlo without going into how policy evaluation is done. And we can compute what the performance would be for every stochastic policy. And what we find is that the best performance is achieved for some policy around 0.3 or 0.33, which is not a deterministic policy. So here's an example now where stationary stochastic policies can outperform stationary deterministic policies. Again, this does not happen in MDPs or in POMDPs when we are using an agent state. So the basic results of MDPs fail to work in partially observed settings. So what I'm going to do next is spend some time trying to review what are the different solution approaches which have been proposed in the literature to find the best agent state-based policy. And this is the basic diagram that I'm going to be working with. And I have shown that the arrows shown in red can be strict. These relationships can be strictly less than equal to. So first, I'm going to focus on the case where we are allowed to use non-stationary deterministic or non-stationary stochastic policies. The key observation in this case is that if I want to find the best agent state-based policy, then this is actually a decentralized control problem. The reason for this is as follows. Let's think of each agent at each time as a separate decision maker. The information sigma algebra available to it is, let's call it IT, and it's denoted by the sigma algebra generated by ZT. As I argued earlier, in general for agent state-based policies, the information sigma algebra is non-nested. So if the information sigma algebra is non-nested, it's a decentralized control problem. So if it's a decentralized control problem, I can use tools from decentralized control to find agent state-based policies. So one idea that can be used is what's called the designer's approach in the literature, originally proposed by Witzenhausen in the early 70s, and I had done some work on it in the late 2000s, generalizing it in certain respects. So the main conceptual idea is fairly simple. This is the system I have. I have an environment, I have an agent which has an internal state, and agent is taking its action based on its internal state. I think of this problem from the point of view of a system designer, which tells the agent what policies to use to choose its action. This information designer does not get any observation. It's simply telling what policies to use in an open loop manner. The problem from the point of view of the information designer is a centralized stochastic control problem. The information of there is environment plus the agent state is the unobserved state for the designer. The designer does not get any observation, and the designer has to choose function valued actions, which are these policies which tell the agent how to map its local internal state to actions. Since this is a centralized POMDP, I can write down a dynamic program for this. To find the dynamic program, I have to find quote unquote the belief state for the designer. The belief state is simply the distribution of the environment state, which would be in this case the environment state and the agent state, conditioned on the observations, but the observations is an empty set, so it just becomes the unconditional joint distribution of the environment state and the agent state. One can show it evolves in a state-like manner if I give the next policy, and if I look at the expected reward, it's a function of the policy and the joint belief of the environment and the agent state. So based on this, I can write down a dynamic program based on the designer's information state. And the key feature of this designer DP is that at every time we have to solve a functional optimization problem. This is a feature of all dynamic programs that we get in decentralized control. But modulo computational difficulties, we can sort of write down this dynamic program and compute the solution. As I said, this basic idea of writing such a dynamic program goes back to Witzenhausen in 73. Immediately after that was published, it was shown by Sendel how this can be used in POMDPs. And we had used the same ideas for general finite state decentralized control problems earlier as well. This idea has been rediscovered in the AI community under the name of no MDPs. One can look at the dynamic program that we get here, and using properties of that dynamic program, establish that actually, if you're looking at time-varying history-based policies, we do not gain anything by looking at stochastic policies. So the parts shown in red here are also equal. So let me take an example to show how this type of an approach works in practice. So I'm going to look at sequential hypothesis testing with reactive policies. So let's say I'm a situation where I have a binary hypothesis. It's either H0 or H1. I have a binary symmetric channel through which this hypothesis is observed. So if a binary channel, not symmetric, I'm sorry. So when the hypothesis is 0, the agent observes y equals to 0 with probability 0.7. If the hypothesis is 1, it observes y equals to 1 with probability 0.8. And the other probability is flipped. And I just want to decide my action based on the last observation. And there are 3 actions available. The agent can either stop and declare H0, stop or declare H1, or it can continue and take another measurement. The per step reward, if it stops and declares H0 and H1, is essentially, if it makes the right observation, it gets a positive reward. If it makes a wrong observation, it gets a negative reward. And we are saying it's more important to detect or not detect, to correctly detect the hypothesis H1 than hypothesis H0. And if the agent decides to take another observation, it has to pay some cost for that. So the designer's approach says construct the state space, which would be an indicator whether the state has terminated or not, indicator what the hypothesis is 0 or 1, and and the internal state. This is a typo here. This should say what is the last observation of the agent. So the designer's state would be the unconditional probability on all possible realizations of these 3 binary variables. So those are a set of size 8. However, this is a problem in which when you decide to take a terminal action, nothing additionally happens. So all the states where the agent has taken the terminal action can be just think of a terminal state. So effectively, I have 5 states and I have a belief over 5 states. So I can write down a dynamic program. The action space of this dynamic program is going to be the space of all deterministic functions from the observations to stopping and declaring 0 or 1 or continuing. There are 9 such things. So it's a relatively simple thing. And note that I don't need to consider stochastic policies because we have established that stochastic do as well as deterministic. And I can write down this DP and solve it. So here is what happens if I solve this dynamic program. The type of solution that I would get is that at time 1, if the agent gets an observation 0, it stops and declares H0. If it gets an observation 1, it decides to take another observation. At time 2 now, if it gets an observation 0, and that can only happen if it had got an observation 1 at time 1, then it decides to continue again, and this type of thing continues. While if it is getting the flipped observation, it stops and declares H1. And in this particular case, it so happens that the best infinite horizon time varying policy is actually a periodic policy. And the performance that it gets in can be computed, and it is this number. The key takeaway is that sort of when we are interested in the best time varying agent state based policies, these can be computed using designer's DP. It is solvable for small models like this where things were binary valued, but it scales quite quickly for larger models. And the source of the difficulty is that I have to search over functionals while solving each step of the dynamic program. Okay. Any questions before I go further?
No questions. I had one question.
Okay.
In the, I think it's probably in the previous section, but when the system was being learned from the data and you're showing some results about the graphs. Now, what happens when let's say let's say it's an offline setting, and what would happen if there is a partial coverage in the data set when it comes to like
I'm going to take this offline at the end of the talk. In this talk, I'm focusing on the online RL setting, and afterwards I can discuss what is the situation in the offline setting. But I'll focus on the online setting for the purpose of this talk.
Yes. Okay. Thank you.
Right. Okay. So this tells us what to do for non-stationary policies, but in practice, we often like to implement stationary policies because they are simple to implement. So let's try to see what to do for stationary deterministic and stationary stochastic policies. So one observation is that when I'm looking at stationary stochastic policies, and this obviously includes stationary deterministic policies as well, it's relatively simple to do policy evaluation. And in the previous part, I've actually shown this, that if I think of the environment state and the agent state together, that evolves in a controlled Markovian manner. So I can think of this product Markov chain where both these things are jointly determined. Once I fix the policy, I just have a Markov chain which is evolving in a particular way. So I can write down the standard Markov chain formulas for doing policy evaluation over this product space. So we can have policy evaluation for agent state based policies, agent based stationary policies. And this observation had been made in the late 1970s and has been rediscovered independently multiple times. The main implication of this is that if I can do policy evaluation, I can do policy search. The catch is this only makes sense if I have access to the environment state. So this is a planning algorithm, not a learning algorithm. Let's try to use that again in this example of reactive hypothesis testing. The way I'm going to do policy search is this dumb way where I'll just look at all possible policies. So the policy is given by what action to take if you get observation 0, what action to take if you get observation 1. These are PMFs on a set of size 3. I'm going to bin this in certain way, which gives some 10 to the 6 policies, do a brute force Monte Carlo evaluation of all of them, which will tell me within this quantized policy space what the best policy is, and it can be computed, and I can evaluate its performance. Its performance obviously would be worse than the best non-stationary policy within the class of agent state-based policies. Okay. So again, the main takeaway from this is that we can do policy evaluation, and then you can pick your favorite algorithm and do policy search using policy evaluation. Finally, I'm going to talk about how to do search within the class of stationary deterministic policies. And sort of the idea for this is motivated from the following. So let's think of what we do when we have an MDP with a continuous state space. So the standard naive solution algorithm here is discretize the state space. So I construct, let's say, a rectangular grid. With every grid, there's a grid point associated. I'll construct a discretized model, which tells me a reward function and dynamics on these discretized grid points. And I'll compute this policy on this discretized model. And then I'll say, whenever I'm in this any state in this a particular cell, I'll use the policy corresponding to the grid point of that cell. Now, if you think about it, the discretized model is actually a POMDP. The true state is somewhere in the entire cell, but the agent only gets to see the grid point or the index of the cell equivalently. But this thing works we treat it as an MDP, and this works in practice. The reason it works is, or I'll say the reason when the situation when it works well is when we have a fine enough discretization. And when I have a fine enough discretization, the discrete MDP that we are constructing is actually close enough to the discrete POMDP that we have. I mean, in this case, it's actually discrete close enough to the continuous MDP, but the point is that it's also discrete close enough to the discrete POMDP. So the solution that I get is close to the optimal solution. So based on this, we can ask, how can I find good policies if I'm looking for stationary deterministic policy? Similar to what I was doing for state quantization, I can come up with any model for my agent state-based MDP. I can come up with some dynamics and a reward function. And if I pretend any dynamics and a reward function, that will give rise to a dynamic program, and I can find a policy from that dynamic program. The catch is that this policy will be good only if the model that I constructed is close enough to the true model. So if I want to make this thing go through, I would have to formalize what I mean by this. So I'll need to come up with a measure of closeness of models. And it will depend, the notion of what measure I come up with would depend on the type of approximation guarantees that I want to provide. Do I want to get guarantees on absolute error or on relative error and whatnot? And there's a big literature on approximations for MDPs. We would have to see how to extend this to POMDPs. So our main idea, this is in a paper a couple of years ago, which we called approximate information state, is that I know that dynamic programming works when two properties hold exactly. So I'm going to say that a model is an epsilon delta approximate information state, which I'll abbreviate to AIS, if these two properties hold approximately. That is, I can find a reward function such that the expected reward is within an epsilon ball of the reward function that I picked. And I can pick a dynamics function for the agent state such that the true dynamics are within the delta ball of the dynamics that I picked. A nuance here is if I'm talking about distance in probability spaces, there is no obvious way to define that, and the results will depend on the choice of metric that I put on probability space. For a certain class of metrics, without going into details, what we can show is if I construct an approximate AIS, I can write an dynamic program corresponding to that approximate AIS. And if I look at the policy corresponding to that dynamic program, that policy would be epsilon optimal. In particular, the approximation bound would depend on these epsilon and delta parameters that I have in the AIS approximation. And it depends on a property of the value function, which depends on the choice of the metric on the probability spaces. Now, there are two ways to interpret the AIS result. One is to say that given an information, given the state space of the agent state, I want to find the best compression function. But the other is that given a compression function or given an agent state function, I want to find the what the approximation error is. And when we go to learning, we make use of this fact that if I can characterize the approximation error for any state update function, then I can do things like gradient descent to minimize this error and use that to improve the agent state update function. But I'll come to that in a few slides. As I said, the results depend on the choice of metric. We use something known as integral probability metrics, but I'll not go into the details for that. So let's see how this thing works compared for some simple models. So first question, let's ask robustness of model mismatch in MDPs. Suppose there's a real world model. Let's say there's a robot whose policy I want to design, and I'm designing that in a simulation model that I construct for that robot. I find the policy in the simulation model, but I want to use it in the real world robot, and I want to see how well this will perform. We can think of the model mismatch as an approximate information state. And we can characterize what epsilon and delta here would be. And if we take the choice of metric as total variation, we recover classical results for model approximation of Muller from the late 90s. If we take this as Wasserstein distance, we recover the recent results of Asadi, Misra, and Littman, who characterized this for Wasserstein distances. Let's think something slightly more general. The abstract model is maybe constructed through some feature abstraction. And based on the feature abstraction, I also construct an abstract model. And I want to ask the same question. If I determine the policy for this abstract MDP, how well will it work in the true MDP? We can think of feature abstraction as an AIS and compute the appropriate epsilon and delta. When I choose the distant metric as total variation, R bounds actually improve the results of Abel and al. By a factor of 1/1 minus gamma. And when we think of this in terms of Wasserstein distance, we recover the recent results of Gileda and al. In terms of deep MDPs. I can think of solving a POMDP in beliefs where we do belief quantization. And again, belief quantization can be thought of as an approximate AIS, and we can compute the appropriate constants. And in this case also, we improve upon the recent results of François Lavey and all by a factor of 1/1 minus gamma. This improvement is actually based on the previous improvement that I mentioned because they use the previous result to derive their results. But the key takeaway point is that the simple observation recovers or improves upon various approximation results in the literature. All right. So this is what's happening in planning, but what to do with learning. So I'm going to talk mainly about agent state based Q learning and then briefly talk about actor-critic methods as well. So agent state based Q learning is what most of deep RL algorithms are implementing. They take the standard Q learning algorithm, which is shown on the slide here, and just run that and say, we'll look at training curves and hope that it converges to a good solution. The catch here is that the agent state based process is not an information state. It's not a controlled Markov process. So there is no Bellman equation corresponding to this thing. So this is not a stochastic approximation of a Bellman equation. So I cannot use standard tools from analysis of Q learning to say why this thing will work. So the key question is, can we characterize whether this iteration converges or not, or can we identify sufficient conditions under which this iteration converges? And if it converges, can we say what is it converging to? Okay? Because I can have an iteration which converges. If I make everything 0, I'll have convergence, but that doesn't mean that I've converged to a good solution. And as I said, the challenge is that the agent state-based process is not a controlled Markov process, so there is no underlying dynamic program that I can use to find the best policy in stationary deterministic policies. So our main result here is that we show that agent state-based Q learning or ASQL converges under mild condition. We characterize what it converges to. It's not the best policy within pi ft that it would converge to. And then we characterize what's the degree of suboptimality. And we'll use this degree of suboptimality to come up with practical algorithms which improve standard RL algorithms for POMDPs. So let's think of characterization of convergence. We are going to make the following assumptions. We'll assume that the agent is following a behavioral policy mu, and we'll assume that under that behavioral policy, the induced Markov chain of the environment state, observation, agent state, and action is irreducible and aperiodic Markov chain with some stationary distribution. And in this stationary distribution, all environment state and agent state pairs are visited infinitely often. We'll assume there is some learning rate which satisfies the standard learning rate conditions. And under these conditions, ASQL converges almost surely to a solution, and that solution is a fixed point for the model, which I call P mu and R mu, which we can characterize explicitly. In the interest of time, I'm not going to explicitly parse what this P and R is, but it depends on the choice of my behavioral policy and the stationary distribution induced by the behavioral policy. Okay. So one thing to observe is that what we do in Q-learning is then we'll take the greedy policy with respect to the Q function and use that. The greedy policy will always be a deterministic policy. So the best we can hope for is that it will converge to the best best policy within the class of stationary deterministic policies. But we have already shown that stationary deterministic policies may not be as well as non-stationary deterministic policies. So we know that ASQL is not going to converge to the best that I could have done with agent state-based policies. In fact, it may not even converge to the optimal policy within the class of stationary deterministic policy. What it converges to depends on the choice of the exploration policy. So if my exploration policy is not well chosen, then there would be no convergence. No convergence to a good policy, sorry. Now, how to characterize what is the quality of the converged solution? I know that the policy given by ASQL is the optimal policy corresponding to this model P mu, R mu that I had constructed. And since it's the optimal policy corresponding to a model, I can use the AIS approximation bounds to get what the suboptimality gap would be. Note that this gives the gap between the best history-based non-stationary deterministic policy and the policy that I am finding, rather than the gap between the best stationary deterministic policy and the policy that I am finding. So the next question that we ask is, can we do better than this? And as I just said, the limitation is that Q-learning always converges to policies in pi-ft, but this is the worst policy class amongst all the agent state-based policies. So could we learn a policy which is not in pi-ft? I cannot go to pi-nd, the non-stationary deterministic policies, because the class of non-stationary deterministic policies, there are countably many such policies, so I cannot search over that efficiently. So what we do is we restrict to a subclass of that which is finitely parameterized, and an obvious subclass is to look at periodic policies. So periodic policy means I'll follow a policy for time 1, 2, 3, L, then I'll repeat this, I'll follow again from time L plus 1, I'll follow the same policy I was following at time 1, and so on. So for that, we propose what we call periodic ASQL or Pascal, and this is just a sequence of LQ functions where we keep track of which time period we are in, modulo the periodicity of the policy. And we get similar convergence guarantees as before. We can show this converges almost surely now to a solution of a periodic MDP. And the converged policy is going to depend on the exploration policy as before. And we can talk about what is the suboptimality gap using AIS style bounds. And I want to emphasize that sort of using periodicity is not just theoretically good, even sort of in real examples, it works. So to illustrate that, this is a simple POMDP that we constructed. Again, I'll not parse the details precisely in the interest of time. But what we can do in this example is we can think of looking at stationary policies. So I'll think of, for stationary policies, I look at different behavioral policies. Here I've picked 3 behavioral policies at random, and we can run Q-learning for each one of these behavioral policies, and we find that it converges to a certain limit. For this model, we can also find the best stationary policy using the brute force search approach that I had described earlier. And exploration policy pi3 actually converges to converges to a solution. Sorry, this is a typo. These should not be pi1, pi2, pi3. These are the policies that I get when I run Q-learning for pi1, pi2, pi3. And that converges to the best stationary deterministic policy. If I search over policies of period L equals to 2, and again, I pick 3 behavioral policies, and I find corresponding to those behavioral policies what the corresponding converged solution performs. And again, one of these things gives the best solution, which is significantly better than the best we were getting from stationary policies. So not only do sort of non-stationary work better than this, but sort of doing Q-learning with periodic policies gives me better performance. Okay. One can do something similar for actor-critic. I'll not go into the details for this. But all this is sort of good theory, but what does it mean in practice? So let's look at ASQL. And what we are getting in ASQL is this is the algorithm that I'm learning. And the difference between the converged policy and the best that I could have done is going to be some function of these epsilon delta bounds that I had found. And these epsilon and deltas are in terms of how far was the model, what the true model from the model that to which I'm converging, and how far is the true dynamics to the dynamics to which I'm converging. So the idea that we have, which is very simple, is to say that if I minimize epsilon and delta, this will minimize my suboptimality bound. So that should perhaps improve how this algorithm is performing. So we take a standard Q-learning implementation, in this case, R2D2, and we add what we call an AIS block to it. The AIS block consists of an RNN and an AIS predictor. The RNN would just take sort of the R2D2 buffer and using that find a state. This state goes to a Q function and a target Q function, and you do epsilon greedy, and that part remains the same as whatever Q-learning block deep learning implementation does. What we have added is now an AIS predictor. This AIS predictor predicts this R mu and P mu parts of my of what I'm converging to. And then we do gradient descent to minimize the error in doing this. And when we backpropagate the gradients, that is also used to update the weight for LSTMs. And sort of a clean discussion of this in terms of implementation is in the third paper that we had last year in iClear. Now, if we do this implementation, and again, the same type of idea works for your favorite deep RL algorithm, we test it on the mini-grid test bench. This is a family of partially observable grid worlds with increasing complexity. And we compare the performance of Q-learning, like ASQL with AIS, with R2D2, which can be thought of as vanilla ASQL. This is a slightly dense plot, but basically what's happening is we have done this for a bunch of environments in the in this mini grid test suite. There are different choices of metrics that I could have chosen on the probability space, and these correspond to different algorithms, and we are looking at different versions of that. The short summary of this is that when we have simple environments, so environments whose size are simple or the dynamics are simple, adding AIS losses does not give any significant improvement. In fact, in some cases, it makes things slightly worse because I have to train an additional component. But when I go to complicated environments like, let's say, these guys, having an AIS block significantly improves environment. In fact, we have settings where when we go to really complicated environments, that without AIS losses, there was no learning. But if we add AIS losses, we do get learning to a good policy. So with this, I'll conclude, and I'm sorry for being just slightly over time. So the key idea is that we can do a characterization of various ways in which one finds optimal or approximately optimal agent state-based policies in POMDPs. And with we have results which can be used to analyze Q-learning and actor-critic for agent state-based RL algorithms in online RL. And I would like to sort of conclude this by emphasizing that the theory is still in its infancy. There are a lot of interesting questions to be answered. So with this, I'll stop, and I'd be happy to take questions.
Thank you, Dr. Mahajan. We can wait to see if there are any questions from the stream. And meanwhile, I just have this question. Maybe I'm not making the connections yet, but in online RL for MDPs, there is this notion of optimism that that helps the exploring policy to learn the right, explore the right regions when it comes to the Q functions.
Mm-hmm.
Is there a similar notion that is already there or that's applicable to like the approximate information state framework?
Not that we are aware of. You see, the difficulty is in an MDP setting, as long as my exploration policy explores all state action pairs infinitely often, Q-learning will converge to the right Q function almost surely. What happens in the partially observable setting is that for a fixed exploration policy, Q-learning converges to a solution which depends on the stationary distribution induced by that exploration policy. So if I start changing my exploration policy along a trajectory, it's going to change the stationary distribution that I would converge to. And so we have not been able to figure out if there are ways in which you can do exploration which will steer the stationary distribution induced by your exploration policy to the right thing. Because the right stationary distribution depends on the solution to your Q-learning problem. There are a few things that we thought might work, and we tried them, sort of like the obvious type of things. We did not find that any of them work experimentally. So I'm not aware of anything which would allow to come up with more nuanced theoretical justification of how to adapt your exploration policy online for these problems and have guaranteed convergence.
Okay. Thank you. Um, yeah, I don't see any questions from the stream yet.
All right.
Yeah. So like the video is gonna come up, the edited video would come up in a day or two, and people usually go on and watch watch it after. So if
Sure.
any questions comes up, I'll just direct them to you.
Yeah, and free feel to directly write to me also. I'd be happy to discuss. And a lot of what's presented here is in the CDC tutorial that we recently have. So feel free to take a look at that.
Yeah, yeah, thank you. And I think I'll send you an email about the offline RL question that
Yes.
I had, and
Yeah.
we can.
Yes. Yeah. With that, I mean, the short answer is that I haven't thought of offline RL, so I'm not sure of what would work in offline RL on the top of my head. I mean, there is the coverage problem, but there are other issues as well in offline RL. And I'm not sure whether the AIS-like things naturally turn up in that setting or not. So one thing is that in Q-learning, we are not artificially forcing that I want to get bound in terms of AIS. It's naturally happening that you're converging to something which is, since that's a solution to a dynamic program, you can characterize the approximation gap using AIS. So if you have results in offline RL setting, which you can guarantee that you would converge to the solution of, let's say, a count-based model, then perhaps one could characterize what is happening, but it would really depend on the nature of what an offline algorithm for Q-learning, for POMDPs converge to.
Okay. Thank you so much.
All right.
Yep. Yeah. Thank you so much for your
Thanks.
time.
Yeah.
And yep.
Thanks for the invitation. Bye.
It was a pleasure having you. All right, everyone. The edited video would come up in a day or two. So watch out for it and do ask any questions on the comments. I can just direct them to Dr. Mahajan. All right. See you next.